Yes, fine. So we have discussed the numericals based on simple connection. Simple connection, that means the connections which were made up of bolted connections. They were bolted connections and they were subjected to simple force. Simple in the sense axial force. So that is what we have studied, and in that also we have studied very basics of the analysis and design part. And while doing so, we have considered the limit state design method. Okay, that concept is introduced, and with the help of that, we have seen few numerical examples wherein you would analyze and design various joints, and these joints were made up of bolts. Okay, so uh, moving ahead, what we said that whatever we have learned, that was a very basic part, just an idea as to how to identify the number of bolts, how to check the efficiency. And when we talk in terms of design, then we need to take care of few more things, few essential things. And now we will slowly incorporate and slowly understand how uh, these these designs can be extended, and how various other formulations can be used in order to completely design a member. Okay, so for that we need to understand the tension member concept. Last time I think we have seen this tension member. What are the tension member? What are the typical cross sections? And when I'm saying that we are supposed to design a component, that design should be foolproof. Foolproof in the sense that we should not uh, skip any of the components which will cause damage to the structure. Okay. So for that, we should. Yes. Hello. Can you start with the recording? I have started. 1 minute. Let me check. शुरू नहीं हुआ है क्या? Oh, sorry. It is being recorded. Okay. Fine. Okay. So when I say that we need to design any component, we should take care of few parameters. Now, in case of tension member, we come across three basic modes of failure. And if we want to design the member in a complete manner, we need to take care of these three modes of failure. We need to check them. We need to see that based on our calculation, whether the bolts or any fixture, for example, bolts, we can also check it for the welded connection as well. But for bolts, the various types of failure should be uh, assessed. Not only for bolts, but we are also supposed to check whether the members in the form of plates, whether they are able to sustain all the three modes of failures or not. That also we need to check. So, uh, after providing the number of bolts, whether the bolts are placed in a better order, keeping in view the edge distance, the pitch distance. Okay, all these terminologies we have already discussed. I hope you remember all these things. If not, you please go through the discussion, earlier discussion, and try to recollect. Okay, so just for time being, try to understand that whenever we are designing any bolted connection, in that we should take care of the end distance, edge distance, then the pitch distance. Pitch is nothing but the center to center distance between the bolt holes, right? So all these things should be taken care of. Now there is some methodology, some background, depending on which all that edge distance, end distances, minimum values are given. If you remember the pitch distance criterion in your IS 800 2007, what it says, that it should be minimum 2.5 times the diameter of the hole. Am I right? Yes, is this okay? Small p distance should be 2.5 times the diameter of the hole, correct? Actually, there is a background behind this, and mm, this will try to minimize the error, uh, and it will try to minimize the collapse condition. Okay, because remember, any uh, any rupture in any solid plate, है ना? Because what we do in order to create a hole, either we drill that hole or we puncture that hole, isn't it? So because of this, the complete area which was supposed to take part in the load transfer mechanism, now it has been reduced to some effective area because of the presence of these holes. And what will happen, the load carrying capacity gets reduced, isn't it? So the plate which was solid, now it has been reduced to a small plate, and the overall capacity of that plate will again reduce. But even though, if we maintain the distance between these holes, whatever we are providing, in a correct manner, then the collapse capacity, it may be increased. Okay, so for that we need to consider various modes of failure. So let us discuss those. First is known as the gross section yielding. What does it stand for? Try to understand that although steel tension members can sustain loads up to the ultimate load without failure, the elongation of the members at this particular load would be nearly 10 to 15% of the original length of the member, and the structure supported by this member would become unserviceable. Have you understood this statement, what it is trying to speak about? Take example of angle section without any hole, without any hole or bolt connection. And if that angle section, this angle section, if it is tested for tension, that is, it is pulled at one end, what it will exhibit? It will elongate. Okay, and it will carry the ultimate load without failure, but the elongation is of the order of 10 to 15%. And because of which, what do you expect? Because of this elongation, although there is no failure, but by the presence of this elongation, see, it will be something like this. If the member is straight enough, something of this sort, and some pull is applied, okay, if this end is fixed, let's say, okay, this is angle section, and with the help of this pull, this complete area will exhibit elongation, and that elongation may be something of this sort, right? So the mere presence of this elongation will make this complete member unserviceable. So this is what is not at all acceptable. Okay? Therefore, in your IS 800 2007, one formula is given. Okay, and what it says, that in the design of tension member, the yield load is usually taken as the limiting load. That means before elongation, see, elongation कब start होगा? When that stress strain behavior will go into the plastic zone, isn't it? Then and only then the elongation will start. Before that, since the complete material is in elastic state, what it will do, it will try to uh, get deformed into its original position or original shape after the removal of the load. Don't you feel so? It being elastic in nature, it will come back to its original position. Okay? So, as far as the design concept is concerned, what your IS code suggests, that the yield load is to be taken as the limiting load. And based on this concept, the formulation which is proposed in your IS 800 2007, it is like this. That is, TDG is equal to yield stress into the gross area of any material or any cross section rather, divided by gamma m naught. Okay, so because of this presence of gamma m naught, which is the partial safety factor for material, what will happen? This elongation part will not come into picture. Okay, the design will be restricted only up to this point. That is before elongation. But but the material will try to at least yield. Okay, it will try to yield. In case of working stress method, the material is not at all allowed to yield. Okay, before yielding itself, it is uh, provided with the factor of safety. So this is the cross section yielding concept, and one has to take care of this mode of failure. This is again this is a part of failure, isn't it? Although it is getting elongated and it is not getting collapsed, but it becomes unserviceable. And in order to take into account that unserviceability, or to keep in check this unserviceability, IS code provides this formulation. Okay? We will see the application of this formulation in our coming numerical, which I am going to be discussing in the further lecture. Okay? So have you understood this first point? Gross section yielding. This is one of the modes of failure. Okay?
Yes.
Second is net section rupture. What happens? The solid plates, as I have told you, that in order to form the bolted connection, holes are generated. They are driven, isn't it? And the plates, they are frequently under tension, which are under tension. They have bolt holes frequently, because most of the time you will see the connection to be made up of bolts or weld, or combination of both, bolted and welded connection. Okay, so most of the times you will see the plates under tension, they have bolt holes. The tensile stress in a plate at the cross section of the hole is not uniformly distributed in the elastic range, but it exhibits stress concentration adjacent to the hole. See, this is the experimental evidence which has been represented over here. What happens? With the help of pull, which is provided in this manner, the concentration of the stresses are somewhat in this manner. And what do you observe? That uh, the peripheral area around the bolt hole, it experiences maximum stress as shown in this figure. This is an experimental evidence which I am showing, and this has been represented in the form of some diagrammatic representation. Now, over here, as you can see, around this periphery, the stresses are more. They are concentrated in, and the intensity is quite more. And at the plate end, you will see uh, the non-linear variation of this stress. And at this point, or at this point, at the edge of the plate, the stress concentration reduces. Okay, so it is non-uniform. Okay, and this, what you observe is in the elastic range. Okay, the ratio of the maximum elastic stress adjacent to the bolt hole to the average stress on the net cross section is referred to as stress concentration factor. Okay, somewhere over here, the average stress parameter, that ratio is called as the stress concentration factor. This factor is in the range of 2 to 3 depending upon the ratio of the diameter of the hole to the width of the plate normal to the direction of the stress, right? So there is a stress concentration factor which plays a vital role in order to define the stresses which are developed on the periphery. Okay? And this is mostly in the elastic range. Now, if this amount of pull is if it is increased, what will happen? Slowly, in statically loaded tension members with a hole, the point adjacent to the hole reaches the yield stress first. That means with the increase in the amount of pull, and this load, what I am talking about, it is static load. It is not dynamic load. Under static loading, what happens? The point adjacent to the hole reaches the yield stress, that is Fy value. So you can see this much portion, which earlier was the maximum part, now slowly this non-linear variation, it will go into the plastic range. And based on our earlier assumption, if you remember, what we do, uh, we convert that non-linear part into linear part, okay, in order to simplify the things, right? And because of which you can see over here or over here, the linear variation is observed. Or in other terms, this variation of the stress has entered into the plastic zone, and therefore we call it as the elastoplastic zone. And this elastoplastic zone is observed when we increase the amount of pull. With the further increase in the pull, what will happen? The until the entire net section at the hole reaches the yield stress Fy value. So slowly, with the further increase in the pull, the Fy value is reached, and this Fy value from this periphery of the hole to the end of the plate, it will now be consistent. Okay, constant Fy value is reached, and this is known as the complete plastic zone. Okay, with the further increase in the pull, what will happen? The rupture or the tension failure of the member will occur when the entire net cross section reaches the ultimate stress, that is Fu value. Right? So slowly what will happen after with the increment in the load, the stress concentration in the periphery, first of all, it will reach up to its yield value. Slowly that yielding will be transferred to the end of the plate, and a point will come that it will reach up to its ultimate strength or ultimate stress value. Okay? So this is the ultimate condition, what you can say. So step by step, the representation of this figure, which was in elastic range, with the further increment in the load, the variation of the stresses can be observed like this. Now, based on this, there is one observation. Since only a small length of the member adjacent to the smallest cross section at the holes would stretch a lot at the ultimate stress, and the overall member elongation need not to be large. ठीक है? Meaning of this is very simple. क्या होता है कि with the when this stage comes over here, what do you observe? That only this much portion of the area, that means you can consider itna portion, okay, only this much portion of the bolt that is under Fu value. Okay, rest of the plate that is yet to go into the ultimate stress value. Remember, joint or any hole or any portion which is a deduction portion, that portion first of all will experience the ultimate stress. Later on, the complete plate, this complete solid plate will yield. Okay, so the meaning of this statement is same, that since only small length of the member, that means this much from let's say here to here, adjacent to the smallest cross section, that is this, would stretch a lot at the ultimate stress, and the overall length of the member elongation need not to be large. It won't be large compared to the ultimate stress which we can observe compared to the overall stresses which are developed in the rest of the plate. This is very small. So as long as the stress in the cross section is below the yield stress, hence the design strength as governed by the net cross section at the hole is given by this formulation. This formulation we have already used when we have seen the rupture capacity of the plate, isn't it? So over here, what do you observe? There is one reduction factor in the form of 0.9, and this 0.9 has been introduced based on the experimentation which were carried out on several plates and under several conditions. Okay, so this reduction factor, it speaks about only this much portion, only this area, to be very specific, only this area. Okay, so with the help of the bolt holes, it may be one hole or it may be number of holes. Whatever reduction of the strength with respect to the rupture capacity, it will be denoted by 0.9 value. Okay, if this value was 1, then you would have observed that this formulation would be like this, and actually this formulation is nothing but the rupture capacity of the solid plate. Okay, this 0.9 is actually based on the bolt hole which is present over there. Okay, so therefore the net rupture capacity, or what we call it as the design rupture capacity, is represented by this formulation. Okay, this is just an explanation. You are supposed to consider this formula when you are solving any numerical, but the background is this. Okay, the background is this one. Now we were talking about the plate. Similar type of situation is observed for the bolts also. Okay, so similarly the threaded rods subjected to the tension could fail by rupture at the root of the threaded region, and hence the net area is the root area of the threaded section. So similar type of stress variation can be observed as far as the bolt is concerned if it is subjected to tension force. Okay, so you can see this elastic variation, and the variation is very evident. That will start from the surface of the bolt hole, rather bolt, that is the thread, and it will vary linearly in the decreasing manner at the center of the bolt. Okay? But this stress variation under the ultimate capacity will be something of this sort. Okay, it will reach to its plastic stage, and then the failure may take place. And therefore, the design tension of the plate with hole or the threaded rod could also be governed by yielding of the cross section beyond the thread, above which the member deformation becomes large and objectionable, and the corresponding design load is given by this formulation again. So over here, since there is no deduction of any value as far as the bolt is concerned, isn't it? Bolt will be a solid part. It will be a homogeneous unit. And if that bolt is subjected to some pull, that capacity of the bolt will now be governed by its yielding capacity or yielding strength, yield strength. And it will certainly behave as if it is a thin plate. And therefore, you will see this formulation of cross yielding uh, is same as what we have discussed earlier for plates. Is this okay? Okay. So this is the second failure that we need to consider. Earlier, if you remember, we have not discussed about these modes of failures, isn't it? We have simply said that, okay, these are the formulations for VDSB, VDPB, and based on that, we have calculated the number of bolts which are required. But after placing these bolts, naturally, these bolts may experience certain yielding. Also, the plate may experience rupture. So all these rupture capacity and the yielding capacity of the bolt and the plate, they are supposed to check. They are supposed to be checked. In addition to this, now the third part is of block shear failure. A statement is given, a tension member may fail along end connection due to block shear. So what is this block shear? Just try to understand. So one video, as you can see, this plate is subjected to pull. So you can see the arrangement, and now you can see. Yes. Please observe this video carefully. So what did you observe in this? See, uh, this is the connection. Typically, you will find such kind of connections. They are available. They are present, and you can see this in this UTM. You can say this portion of the plate or the connection. This is getting pulled in the upward direction. This is fixed. So the uh, section which is subjected to the pull, it is this one and this one, right? In this case, as you can see, slowly because of the presence of the loading, what happens? Bearing starts. Bearing in the sense the plates get connected to the bolt, okay, or they are in contact with the bolt, and because of the presence of this connectivity, bearing starts. And now see what happens. Okay, so now are you able to see that there is a failure of this plate, and the pattern of the failure is something of this sort, isn't it? Are you able to see this failure pattern?
Yes, sir.
ठीक है, ठीक है. Uh, Still it will fail. ठीक है. So see what happens with this nature of the failure, whatever you have observed. Here you can see that this portion, it will consist of plate. That is the plate which is somewhere over here, this portion plate. And this failure, since it is associated to the pattern which represents a block, it is known as block shear failure, because the failure is in the shear plane, as you can see. So there are two shear planes. One is this and another one is this one, as you can observe over here. यहाँ का एक shear plane हो गया और ये यहाँ का shear plane. So there are two shear planes. One is known as the weaker plane, and another one is known as strong plane, that I will discuss. But have you understood this failure pattern? These are observed. Okay, these are very much there, and because of the presence of such kind of block shear failures, we should consider this the values or the criterion which are given in your IS code in order to check whatever connection we are providing for block shear failure. Okay, so I hope you have understood this failure mode. This is one part. Okay, ये तो एक type हो गया connection का. As I will proceed, you will see that there are different connection types and for different members. This is for two plates which are connected to this another plate with the help of bolts. Now let us see another video. So this is a plate which is subjected to a pull, and now you can see there are actually different modes of block shear failure. ऐसा नहीं है कि ये एक ही पैटर्न आपको available रहे. You can see various modes of failure in this particular animation, you can say. So mode 1 was represented. Mode 2. In mode 2, what happens? In mode 1, this you can say that this type of failure is observed. In case of mode 2, the central portion of the plate and the rest of the plate, it will come out or it will fail. Okay, remaining these two portions, they will be as it is connected to the connection. Then the third mode. Okay, this is also possible. This type of failure again, it's possible, right? And the mode 4. Okay, so have you understood? For block shear failure, there are again different modes of failures. 4 basic modes, as you can see over here. This is mode 1 failure. Depending on the connection design, there are several mode of failures. This is mode 1. तो आप देखो हर एक मोड में what do you observe? That there are two shear planes. Can you see this? This is shear plane number 1 and this is shear plane number 2. Are you able to see this? Yes? Yes or no? Okay. So this is mode 1 failure. Even in mode 2, you will find there are again two modes of failure. So see, this is 1, this is 2nd, correct? Then third mode, something of this sort. Again, there are two modes of failures. And fourth mode. So I hope you have understood a little bit related to the modes of failure of for block shear. Okay? Now we will see the application of this and what IS code recommends and how to make use of these formulations that we will see in the numerical part. But just try to understand, depending on the different modes of failures, we can now summarize. What it says that when applied tensile load is increased, the fracture strength of the weaker plane is approached. However, this plane does not fail as it is restrained by the stronger plane. Okay? The load can still be increased until the fracture strength of the stronger plane is reached. During this time, the weaker plane yields. तो इसमें दो आपको terms add हुए हैं, एक है strong plane और एक weak plane. Now let us try to understand what is this strong plane, rather weak plane and strong plane. ठीक है? So देखो, video तो मैंने आपको show किया. Now I will correlate that video with the help of this diagrammatic representation which is given in your IS code. देखो ये पुल है, and this pull is getting applied to, let's say, for this plate connection. As we have seen that there are different modes of failures pertaining to this plate connection. ठीक है? In that case, ये जो plane आपको दिख रहा है, this is known as the weak plane. Why weak plane? Because this plane will be the plane which will be subjected to the pull first, isn't it? It is very much simple to understand, right? And because of this 1 and 2, this plane becomes weak. Similarly, 4 and 3, it becomes weak. And this is very specifically, I am talking about the plate connection only. The first video which I had shown to you, plate connection. Okay. So for plate connection, these two planes become weaker plane. Now this weaker plane is accompanied with this stronger plane which is perpendicular to the direction of the force which is getting applied. What happens as per this statement? If the tension load is increased, first of all, this weaker plane will experience ultimate stresses. But the failure is restricted because of the presence of this stronger plane. Before failure, what will happen? The stresses will reach into this stronger plane, and now this strong plane will be subjected to the yield stress. With the further increase in the loading, this yield stress capacity is utilized and then it will go into its ultimate stress. And once the ultimate stress capacity of this is reached, that is stronger plane is reached, then the failure will take place. Are you getting me? Did you get the sequence of failure? How the failure may take place? Are you getting me or not? ठीक है? So see, first yielding will start for the weaker plane and it will reach to its ultimate capacity, but the failure will not take place for the weaker plane. Why? Because of the presence of this perpendicular strong plane. So what will happen? The stresses will be distributed in this strong plane, and with the further increment in the loading, it will go into its ultimate stress. First of all, it will start yielding and then it will go into ultimate stress. And as you have seen in this earlier video over here, so you can see the process is quite, slow. It is not all of a sudden, it is gradual. And because of that slow process, you can understand that first of all, the weaker plane is subjected to yielding, then the load is transferred or the stresses are transferred to this stronger plane, it will start yielding and then it will fail. So let us observe that. Okay, let us observe. The force is getting increased, increment of forces there. Video है. Now see, समझ गए आप लोगों को? ये देखो ये फेल हो गया, स्ट्रॉन्गर प्लेन फेल हो गया, उसके बाद ये वीक प्लेन जो है ये शेयर हो जाएगा. गॉट इट? ठीक है, फाइन. So based on this, IS code, what it recommends, it considers the contribution of both these planes. और उन्होंने बहुत सिंपल फॉर्मुलेशन प्रोवाइड किया हमको. उन्होंने लीनियरली उसको ऐड कर दिया है. Although it is not that simple, but because of the modification of that elastoplastic stress strain curve, this linear expression can be achieved. तो उन्होंने क्या किया है देखो, the block shear capacity which is represented by TDB. TDB is known as design block shear capacity. What it says, AVG into Fy divided by under root 3 gamma m naught plus 0.9 times ATN into Fu divided by gamma m1. So we should understand what are these terms, AVG, ATN. AVG is nothing but minimum gross in shear along bolt line parallel to the external force. That is this, parallel to the external force. This is the minimum gross area in shear. Okay. What is ATN? ATN is minimum net area in tension from the bolt hole to the toe of the angle perpendicular to the line of force as shown in figure. So we will also see what is the effect for the angle section. Whatever I have discussed, this is especially for the plate member. एंगल सेक्शन का मैं डिस्कस करूंगा आप लोगों के साथ, ठीक है. So both these things have been added, and while adding, you can see this 0.9 term has been introduced. Why? Because there is a presence of bolt hole, and as we have seen earlier in the discussion, why this reduction factor has been introduced, to take into account the ultimate failure capacity of the bolt hole, stress concentration around the periphery of the bolt hole. That 0.9 term has been introduced. Okay, so in the next class we will see what is the effect of this block shear for angle section. We will try to understand. I hope you have understood this concept to some extent, not completely, but to some extent. Is this okay?
Yes.
ठीक है. So I will stop here, and in the next class we will meet and we will discuss about the rest of the portion. Thank you.